All right, so we've been talking about solutions in Unit 5. I gave them all away. So, did you get one on Thursday or on Wednesday?
Yeah, I did. I just didn't have it. That's all right, just wait it.
Okay, so we've been talking about solutions. Remember the two components of a solution? Solute and solvent. Which is the smaller quantity? Solute. And the solvent is usually liquid. Yes, and unless we explicitly state otherwise, assume the solvent in all cases is going to be water. So, if we don't say, it's very safe to assume that it would be water. So we're going to talk about solubility now and how it relates to solutions. There's a lab 19, that involves solubility, graphing solubility, and this is a lab that can be done completely outside of lab. You have all the data within the lab to answer the questions. But after we go over these terms, it will be much easier to answer those questions on graphing solubility. So if you looked at it and I have no idea what this lab is, that makes perfect sense because you haven't covered it yet. So we're going to talk, I'm going to give you the definition for solubility. And by the way, I had spoken to a student about this before. Anytime I give definitions, if you find yourself struggling on true, false, or multiple choice questions, you could make a note card for the definitions. Also, look up the definition in your textbook to see what that definition says, so you can hear it many different ways. So then on true, false, and multiple choice questions, it really jumps out because you're so familiar with all the definitions. So just a study tip. Okay, so here's a definition. Solubility is the maximum amount of substance that will dissolve in a given amount of solvent at a specific temperature. Yes, exactly. So the maximum amount of substance that will dissolve in a given amount of solvent at a specific temperature. So this is like the question that Jay asked last week about sugar, making it more soluble, and the iced tea. If you heat up the tea, you get more sugar dissolving. So solubility is temperature specific. And you'll find this when you work on the graphing solubility lab, that, at different solubility, or at different temperatures, there are different solubilities. Usually the way it works is the higher the temperature, the more solute will go into solvent. So I'm going to give you some terms related to solutions. So these next three terms are usually used to describe solutions. So you say an unsaturated solution. So what is an unsaturated solution? This is a solution which can dissolve more solute. So with this iced tea example, this is where you've added the sugar and it's still, you don't see any going to the bottom of your iced tea. You can still add few more teaspoons, tablespoons, cups of sugar, depending on how much sugar you like in your iced tea. Unsaturated, you could still put more sugar in, like I mentioned. Now, saturated. This is a solution which contains the maximum amount of solute that is able to dissolve. So with this, a saturated solution, if you were to add a little, like even a granule of sugar, it would go to the bottom. You see what I'm saying? So it's not, it's all dissolved, but then when you add more, it goes to the bottom. So you'll see, that's when if you were adding cups of sugar, you would just, you'd be stirring it. And, I feel the sugar at the bottom. So now, supersaturated solution. This is an unstable solution. So I'm going to put unstable in parentheses. This is a solution that contains more solute than the saturated amount. So I say it's unstable because it won't stay dissolved. Eventually it will crash out, right? It will come out of solution. Has anybody made like rock candy? Yeah, so at a certain point it's all liquid, and then it just, after you have it cooling down for a while, it crystallizes. It's pretty cool to see.
That's
Super saturated, at that high temperature, when you're coming down, the temperature is decreasing, and so it may be that it's still molten, and then it reaches a point where it's no longer in solution.
My family does something like that. It's some kind of Cajun recipe. I have no clue, but it's like 20 pounds of sugar in a bite. It's not like a praline, but it's like you just keep heating up like sugar, and it pretty much gets to like the consistency of like fudge.
Yes, very hot.
Yeah, it's like it starts getting in blocks, and it feels like you're really not in sugar.
I get, if I eat too much sugar, I get chills. I don't know if anybody has that too.
It'll give you a stomach ache, and my aunt seems to just like throw down like a dozen of them.
How much is too much in your house?
Well, it depends. Like if it's a really rich dessert, like just a slice of cake, like a few bites into it, I just get, I don't know what it is. It's weird, but then my husband, he could just eat the whole thing, and not have any. But it's some things I can eat a lot. I don't know. It's strange. Everybody's has a different sugar tolerance, Then some people, it blows me away who have no interest in sugar. I know. I know. It's too. It has such a pull on me. So, on the next page, I have these general things that you can think of. When you have a solid dissolved in a liquid, as temperature increases, solubility increases. So that is definitely the case with sugar. As you heat up, whatever the butter, maybe your recipe calls for that, or the water, or whatever, you're going to be able to add more sugar as the temperature increases. Now, so for a gas dissolved in a liquid, now think about the substances that we have that are gases dissolved in liquids. What would those be? Like, the one thing I always think of is soda. Because the carbonation, that's gas, CO2 dissolved in liquid. That's what gives it that fizzy feeling. And so, if you had a choice about whether you leave your soda that you've just opened, it's just made that satisfying, either the can opening or the lid opening, would you prefer to leave it in a cold environment, or would you prefer to leave it in a hotter environment? Which is going to go flatter first? The hot, exactly. So for a gas dissolved in a liquid, as temperature increases, solubility decreases. So I'll put in parentheses soda pop.
That's why it explodes.
Mm-hmm. Right, if it's sealed, Yeah, no, I can tell I've lived in Kansas for over 10 years now because I say pop. Growing up in Virginia, everybody would say Coke. Say, would you like a Coke? And my parents would always, if I had friends over this, would you like a Coke? And then my friends, they would I could just see the look of disappointment when they were offered a Diet Coke. They're like, what? That's not a Coke. That's a
Pepsi
Diet
doesn't exist in the South.
No.
That was a shock to me.
Mm-hmm. So, but yeah, soda pop. No.
Where from in Virginia?
Lynchburg, Central Virginia.
Lynchburg?
Mm-hmm. Yeah, it's very hilly there. So when I hear people talk about hills here, but it's the city of 7 hills, and it really is. You'll be driving, and your stomach just, when you're driving down these hills, oh my gosh. But fortunately, we don't get very much snow there. It's more ice once every 10 years, something like that. But all right, we are getting. So we're continuing our discussion of solutions, and one of the things in Unit 5 that's like the must-do thing. These solubility rules. And a lot of times students are like, no, I don't want to memorize those, but it is really hard to do well on your exam in Unit 5 if you don't know these solubility rules. And one of the reasons we're going to learn chemical reactions that rely on these solubility rules to predict them. And our lab, Lab 17, solubility rules, will cover this. And so as long as you know these reactions, you will be able to predict, or as long as you know these rules, you will be able to predict the reactions. So we probably have 20 to 24 points on the next exam that's devoted to reactions, kind of like what you've had for organic in Units 3 and 4. And I would say, if it's 5 questions, probably 4 of the 5 questions rely on these solubility rules. So if you have to make up a song, if you have to write these over and over again, commit these to memory. They are worth it. So in these rules, you'll see and hear me state salt. And, when I hear salt, I think of table salt, just sodium chloride. With these rules, and in inorganic chemistry, when you hear salt, it's really just an inorganic compound. So, inorganic compound. So it's ionic. And this is a review from Unit 2. What atoms are involved in an ionic compound? What's that?
Did you say atoms?
Yes. Metal to non-metal. Yes. Excellent. So you have a metal to non-metal or any of those polyatomic ions. All right. Now, this S in parentheses, we saw this in lab. This stands for solid. And in terms of your solubility rules, you have to be very careful because solid means insoluble. In other words, not soluble. And I caution you, I see so many students get confused with this S because they think S means soluble, right? So be careful. Whenever you see S, that means solid, that means insoluble. And tonight in lab, we will see the solids form, and we'll see, how that influences our reactions. But whatever you need to do to convince yourself that that S does not stand for soluble, start thinking of it now. What does AQ stand for? Aqueous. So very good. AQ. Aqueous, that means soluble. Okay, it's dissolved in water. So this is soluble. Dissolved in water. All right, so here are the solubility rules. Sometimes I feel like these are the side effects listings, you get on drugs, these listings, like, no, accept this, with this. So, and you're questioning, what exactly does that mean? So if these rules seem kind of crazy right now, they are. Just kind of take them at face value. We will start applying these rules, and then you will see, okay, now I know what she meant when she said this. So salts that contain lithium, sodium, potassium, rubidium, cesium, ammonium, nitrate are always soluble. So soluble, what symbol does it get? AQ. Now, what group are lithium, sodium, potassium, rubidium, cesium? What are those ions in? So, right, so the group 1. Excellent. So you can simplify this rule by saying salts that contain group 1 ions, ammonium, and nitrate are always soluble. The second rule, salts that contain chloride ion are soluble except silver chloride and lead 2 chloride. So if everything is soluble, what symbol does that get? AQ. Excellent. And then what would be next to AgCl and PbCl2? S. Good. All right. Salts that contain, what's this ion here? Sulfate, good. Salts that contain sulfate ion are soluble except, so that gets the AQ, except barium sulfate, lead 2 sulfate, calcium sulfate. So all of these, all of the exceptions to the rule get an S. Okay, so the last rule, salts that contain hydroxide, what's the name of that one? CO3 minus 2. Carbonate, good. S minus 2 would be sulfide ion, good. And then PO4 3 minus would be phosphate, good. So all of these are insoluble. So what symbol does insoluble get? S. Except those with lithium, sodium, potassium, rubidium, cesium, or ammonium. So, except those paired with group 1 or ammonium. Group 1 or ammonium. Now, I often get a lot of questions. Why in that last rule don't you have nitrate ion listed, right? Why isn't that the exception? Yes. So it's negative, very good. So you're not going to have a negative going with a negative, right? So that's why it's not listed in the rule. So on the bottom of page 6, I have salts, right? Remember, salts are inorganic compounds. And my question to you is to circle the insoluble salts. What symbol would insoluble get? S, good, very good, solid. So what I find myself doing still, after teaching chemistry for all these years, I find myself repeating these solubility rules over and over again. Just as I come across a compound that I need to predict whether it's an S or an AQ, I refer back to those rules. So, if I was given a list, and especially if I was given a list on a test, and there was a time constraint, I would try to very quickly eliminate ones that are soluble, right? That would probably be my most efficient use of time. What ions do we know of that are always soluble? Group 1 or there are 2 other ones, ammonium or nitrate. Excellent. So if you see any of those listed, not a possibility. So like this first one, well, that's group 1. Can't be. Cross it out. Ammonium, there's ammonium. Okay, if it's not group 1 or ammonium, I'm going to skip over. I'm not going to do anything with it right now. I'll come back to it. Okay. So we eliminated a few.
Top row.
Top row.
Second from the right. Is
Rubidium, yes.
bottom row is
Sodium. Any others? So we got rid of 4. Now it's probably a good idea to go through and, you could do specific, like you could do the second rule, salts that contain chloride. So we have, this one contains chloride, chloride, chloride. So salts that contain chloride are soluble except for AgCl and PbCl2. So here we found 2. that are insoluble. And then what about iron 3 chloride? It's going to be soluble, so it won't get circled, okay? Good. All right, so you can go next to the sulfates. Okay, so salts that contain sulfate are soluble except barium sulfate, lead 2 sulfate, I don't see any lead 2 sulfate, and calcium sulfate. So these other two I can cross out because they're not. Right, now the remaining ones that aren't circled or X'd out are rule number 4. Salts that contain hydroxide, carbonate, sulfide ion, or phosphate are insoluble except those with group 1 ammonium. So we already went through and got rid of our group 1 and ammoniums, right? So this is going to be insoluble. This is going to be insoluble. So strontium hydroxide insoluble, aluminum sulfide insoluble, magnesium phosphate insoluble, calcium carbonate insoluble, magnesium chloride. So, oh, I missed this chloride. We've got to go back to our chloride rules. So salts that contain chloride are soluble except for AgCl and PbCl2. So cross it off. Good. So does everybody follow along with how to kind of classify soluble or insoluble? All right. This skill is very important in predicting reactions. So coming up, we have two types of reactions where the solubility rules influence the result of the reaction. So with dissociation reactions, remember that dissociation is another word for ionization. We learned about ionization last week, so you can say ionization reactions. So with these reactions, you put an ionic compound, and all of these ionic compounds are going to be solid. Before you put them in water, if it's an ionic compound, previously what we saw was that it was always going to ionize. If it was metal to nonmetal, it would always ionize. Now we have to consult the solubility rules. If it's an ionic compound, if it's soluble, then it will ionize. So the good news is you could get a no reaction on an ionization reaction. So if you have a compound that is insoluble, what's the symbol for insoluble? S. There is no reaction. So this is where you get to write, remember the no reactions from organic chemistry, that's where you get to write a big NR. You can move on. However, if a compound is soluble, what's the symbol for soluble? AQ. It breaks down into its component ions. So we'll go through a few. What's the rule for chlorides? All chlorides are soluble except for 2. Ag, Pb. Okay, so this is insoluble. So because it's insoluble, what will happen when you put it in water? It's just going to go to the bottom, right? There's going to be no reaction. So, if you were to use a conductivity meter to measure whether you had a strong electrolyte, weak electrolyte, or non-electrolyte, with these insoluble ionic compounds, you would get very little electricity being conducted, because it would just be from the residual amount in the deionized water. Because silver chloride is just going to go to the bottom. It's not going to ionize at all. It's not going to dissolve because it's insoluble. So another chloride. All chlorides are soluble except for what two? PB and Ag. And by the way, I'm going to say these rules a million times, as much as I possibly can. So if you get tired of me saying them, that's good, because I'm doing my job. I want you to hear it over and over again. So is this one soluble? Yes, it is. So that means this is going to break down into its component ions. And the symbol next to those component ions will be AQ. Excellent. Okay, so how do I figure out what the component ions are again? Do the cross and raise. So this will be Fe plus 3, and that will be AQ plus Cl minus AQ. Now, is this reaction balanced? You have to put a 3 on the Cl. Excellent. Now it's balanced. All right, I'll do one more with you, and then I'll have you work a few on your own. So this is the fourth rule. So that's the one, salts that contain hydroxide, carbonate, sulfide, phosphate are insoluble unless paired with group 1 or ammonium. So yes, it's not soluble. It's not group 1, it's not ammonium. So that means it's insoluble. You get no reaction. Now on the exam, if you want to write like a little arrow, write insoluble, if that helps you, by all means do it. I will give you full credit on that. I'm not going to say you just have to write NR. The reason I'm starting to do this is because I want you to think of, you've taken the solid from a bottle, you've mixed it with water, and even when you mixed it with water, it still remains insoluble. So it still goes to the bottom. There's going to be no ions that are formed. Okay, so we have 4 reactions left. I want you to go through and try them on your own. You're going to be referring back to your solubility rules. Any no reactions here? Yes. Which one? Excellent. So all sulfates are insoluble except for barium, calcium, and lead. So this one would be insoluble, and that's why you get no reaction. The other 3, they're all going to be soluble. This is group 1. Sodium is group 1, so that makes it soluble. Remember the rule with chlorides, all chlorides are soluble except for Ag or Pb, so that's going to be soluble. This last one, all sulfates are soluble except for, what are the 3 again? Ba, Ba, Pb, Ca. So because of that, these are all soluble. So we would have Na plus 1, AQ, SO4, minus 2, AQ. Is it balanced? Put a 2 in front of the sodium. Excellent. 2 in front of the sodium. All right, this next one. What's the charge on copper? Copper plus 2, aqueous plus Cl minus 1, AQ. Is it balanced? Put 2 in front of Cl. Good. And this last one, what would the charge be on silver? 1 plus 1. So, this is an excellent review of Unit 2. So you are studying for the final right now by working on Unit 5. To figure out the charge on silver, you're going to do the cross and raise. So sulfate is -2. And you might think, oh, well, silver is +4. But remember with polyatomic ions, when you just have one polyatomic ion, there are no parentheses. So there's just one sulfate. So if you want to think of it, if it helps you, you can put a parentheses around sulfate and just have a 1, when you're doing the cross and raise, just to be sure. And as you work with these, the more confidence you have, you won't have to put the parentheses. But especially when you're starting out and you think, oh, that doesn't sound right. Silver's not +4.
Isn't silver one of the weird ones we have that's only +1?
Right. Silver, it's in the transition metals, but it only has one charge. That's right. So that's AQ, and then sulfate, -2, AQ. Is it balanced? How would it balance it? 2 to the AG. Good. So dissociation reactions, also known as ionization reactions, these are the ones that can be influenced by your solubility rules. The other set of reactions that can be influenced by your solubility rules are precipitation reactions. And another name for these reactions is a double displacement. Now when you hear precipitation, what do you think of? Rain. Yeah, so you think of this rain or maybe snow, depending on what season you're in, you think of rain or snow. In chemistry, when we say precipitate, we mean a solid. So these are reactions in which a solid forms. So these produce a solid. What's the symbol for solid? S. What's the term from our solubility rules that means S? Insoluble. So another name for these reactions could be the insoluble reactions, right? In order for these reactions to occur, something has to be insoluble. So insoluble reactions. So double displacement, kind of a general term that describes what's going on in this reaction. You have two couples that are dancing, they switch partners. This is what's happening in a double displacement reaction. You have your cation going with an anion, so you have A going with D, and then you have C going with B. And we always write cations first for these formulas, so it's going to be CB. I know because of the way I have this reaction set up, you think it should be BC. You want to put it in alphabetical order. But we write cations first, anions second. So in order for this reaction to occur, in order for it to be an insoluble reaction, what do we have to get? One of those products has to be a solid. Just one, not both. In some rare cases, you can get both solids, but most often, all you will see is one producing a solid. And that's all it takes for this reaction to go. So, and you guys will be able to predict which one it is because you know your solubility rules so well, right? So you'll get to that point. You will. So if both products are soluble, there is, what do you think? In order for it to be an insoluble reaction, you have to have a solid. There's no reaction if both products are soluble. So remember that both products being soluble, what symbol goes by soluble? AQ. Yes. So if both products are soluble, there is no reaction. If either or both products are insoluble, that's S, there is a reaction. So I'll go through this one, and then we'll see this again the next time we meet. So this is what you would see on a quiz or an exam. I would give you the reactants, and I would expect you to give me the products. It helps. The first step is to determine the ions and the reactants. So if you write out Na plus, Cl minus, and the ions in this one would be Ag plus, NO3 minus. Then you're going to have them switch partners. So the sodium is going to go with the nitrate. What would the formula be for that? NaNO3. And then the silver is going to go with the chloride ion. So what would the formula be for that one? AgCl. Okay, so you've determined the ions and the reactants. The second step is to do a double displacement to determine the possible products. Remember, cations are always written first in the formulas. Now, I want to say right here, if you had written AgCl first and sodium nitrate second, that's fine. As long as both of those products are on the right side of the arrow, on that side of the arrow. But if you had written NO3Na or ClAg, that would be incorrect because the cations have to be written first. All right, so we've written the formulas. These were pretty straightforward formulas because it was a 1-to-1 ratio. You didn't have to do any of that funny cross and drop business. The third step when doing these reactions is to determine the solubility of the products. If they are all soluble, remember soluble gets AQ, then there's no reaction. All right, so what do you know about sodium nitrate? That would be good. AQ, soluble. What do you know about silver chloride? Non-soluble. So what symbol does it get next to it? S. So good. So does this reaction proceed? Absolutely. So before you waste time trying to balance this equation, determine if it proceeds first. Because if you write your products and they're both AQ, you can just cross it off and write no reaction. But, if you continue balancing and then at the very end you say, oh, they're both soluble, there's going to be no reaction. You've spent time balancing when you didn't need to. So the fourth step is to balance the reaction. This reaction, the first few that I do, I try to keep pretty simple. It's just a 1-to-1, so we shouldn't have to balance, but let's double check to be sure. 1 sodium, 1 sodium, 1 chloride, 1 chloride, 1 silver, 1 silver, 1 nitrate, 1 nitrate. So this is all balanced. And you can leave the coefficients blank or you can put 1s. So we'll stop here.